Well, ladies and gentlemen, your questions, if there are any. Well, in that case, we have no questions so far. Let us continue. So we had first a DC transmission, which we have established on the right panel. Then we have an AC low frequency transmission, and we have seen that the maximum power handling capability to the same load has been decreased by a factor of 2. And now let's have a high frequency transmission where standing waves might happen. Now let us consider now a termination of the coaxial cable, which would be 2 times the characteristic impedance of the cable. So if we have a 50 ohm cable, now we will deliver the power to a 100 ohm load. I will have to switch a little bit paper. So we now have the line which is 50 ohm, and we would deliver to a load which would be 100 ohm. So this is not a good impedance match, and we will have standing waves there. How strong standing wave? Well, we would have a reflection coefficient of 100 minus 50 divided by 100 plus 50, which is 50 over 150, which is 1/3. So 1/3 of the voltage would reflect back. Now this would give rise to a standing wave ratio. The standing wave ratio on that line would be equivalent, well, the maximum where those two waves add happens at some location, and those two waves that add, one is the magnitude of incoming voltage, let's say 1, and the other has the magnitude of R. So that would be 1 plus R, that's the maximum voltage, and the minimum voltage would happen at the place where those two waves are antiphase. So the denominator would be 1 minus R, which gives you the estimation or correct equation for the standing wave ratio for our case, which is 1 plus 1/3, that is 4/3, 1 minus 1/3, that is 2/3, which is the standing wave ratio of 2. So the maximum and minimum voltages at this transmission line would be with the ratio of 2. And that means that if you, let us consider that you put the same voltage at the input of the line as we did in the AC case. So that means that we would have now there the voltage of the propagating wave and that of the reflected wave. So we would overshoot the maximum voltage available or allowed at this line, and it would break down. So we would have to decrease the input power. How many? Well, 1 plus 1/3 times the input power, or 4/3 of the input voltage, should be equivalent to the maximum. So we would be only allowed to put there 3/4 of the original voltage. So that's the first point. Now, this is not the total thing. We would put there this amount of voltage, and the power delivered to the load in AC case without considering standing wave ratio was, let's say, this one. Now we would have to decrease decrease voltage at the input, and we would have to do that so that the input voltage times 4/3 is the maximum voltage, which means that our new input voltage is only 3/4 of the original maximum voltage. So this is the first loss we have occurred. Now this is not the whole because we would have, at this case, the power that we input by the generator into the line, but some of that power will reflect back. And so we would be only able to get into the load a part of that power. At the load, we would have some voltage, which would be, we have to draw that. We have the line, and we have the load, and if we draw the voltage magnitude against the z coordinate, and this is the place where the load is, then we would have something like where this is the value at the load. And the voltage at the load is not the maximum voltage on the line. So this is the second power loss we would incur. So we will have to decrease the power that is submitted to the line, and at the same time not the whole power would get into the load. Some of that would be reflected back. Now we can calculate how much power would be reflected back. We have a transmission line, we have a wave carrying some power there, and we can calculate how much power would be reflected back, because the power carried by the wave is proportional to the square of the voltage. So if we have the voltage going there at this level of the original maximum voltage, we would also have the wave carrying back the power, and that would be the reflection coefficient times this voltage. So first the power going there, and I would just mark it by an arrow, power going into the cable, lossless cable, would be smaller than that one in just pure DC case, and that would be the voltage input, the input voltage squared, divided by, of course, 2 impedances of the cable. But now there is a reflected wave carried back from the load by reflection, and this would be the reflection coefficient times the input voltage divided by 2Z0. So just its reflection times lower. And we have to square it, of course, to have the same dimension here. So if we get this into one equation, the power delivered into the load would be, and now we can first put the impedance of the cable into denominator. It's common to those equations. And now we have input voltage squared minus R input voltage squared. So we can put the input voltage squared 1 minus R squared, and this is the amount of power that would remain in the load. Now we should possibly do a short calculation for our 50 ohm cable that has been terminated in 100 ohm load. Now to compare those three cases, we should possibly also do that for the DC case and the pure alternative current case. So let us put there by red the change. Let's first consider that we had, as you remember, a 50 ohm cable supplying power to a 50 ohm load in DC case. So let's now find out what happens if the load increases twice. So the first power was voltage squared dividing by 50. If we increase the load twice, it would be voltage squared divided by 100, which would be 0.5, 1/2 of the original power delivered to the load in the DC case. Now we have in AC case, if we double the resistor, it would be again 1/2 of the original power. So if we compare it to the DC case, it's 0.25 of the power delivered to a 50 ohm load in DC case. And now we will have to get a calculator and do some calculations here. So first we have the reflection coefficient, which is 1/3. Now this is quite a small reflection, as you can see. A standing wave ratio of 2 seems to be a lot, but it could be even worse. So this bracket turns into 1 minus 1/3, which is 2/3, and 2/3 sorry, there is a mistake. It should have been like this. The square should be here. So this bracket is 1 minus 1/3 raised to the second power, which is 8/9 of the input power. That seems very good so far. So we would have But now we have to consider that the input voltage is only 3/3 of the maximum voltage that could be used in the DC case. And this should be input here. So the input voltage is just 3/4 of the maximum voltage, which if we raise to the second power is that the square of input voltage is 9 divided by 16, the maximum voltage squared. So now the power that we deliver to the load is given by 3/4 times 9/16, which is 27 divided by 56, and that should be calculated, which is 27 divided by. And that gives rise to a 0.482, which means that the power delivered to the load through the cable is more or less 1/2 of the power that could be delivered in a DC case without considering standing wave effects. So this comes to a fact that the original cable that could deliver one-half of the load if the impedance increased twice, one-half of the power delivered to the load, but would be anyway only 1/4 of the power delivered to a matched load. And now for this mismatch, it would be not 1/4 but 1/8 of the power that could be delivered to a matched load in a DC case. So this is the result, that any mismatch, that is any reflection on a transmission line, makes problems to radio engineers. And this is not the only case, because in fact power is not that important, well, unless you heat dry wood, heat food in microwave oven, then you have of course an important story with the power. But much more important is information, and any reflection causes distraction of the information that is carried by the electromagnetic wave. But that's another story. In today's story, I wanted to show you that there is some quantity which is called power handling capability of a coaxial line, and this power handling capability is dependent on the maximum voltage that you can put on the line, or that can happen on the line, because you necessarily do not put it at the generator on the line. Due to the effect which is called standing waves, the voltage at some position of the line could be much bigger than the voltage issued from the generator. And this is something you have to handle as an engineer, and you should somehow beat the standing wave ratio so that the maximum and minimum voltage on the line do not differ very much. Now this was not an easy question, and I expect your questions.
Yes, in the last equation, the power delivered to the load. Could you please explain again, like this, the first part there?
Yes, I will get back to a new blank sheet of paper. So we describe the power delivered to the load as the power traveling there from the generator minus the power reflected back from the load. So the power traveling from the generator would be, this is this power. That's the input power, input voltage delivered from the generator divided by two impedances of the line. So that's the input voltage squared divided by two line impedances. And we have to subtract the wave returning back. So minus, and the reflected wave has the maximum, or the voltage is the voltage of the incoming wave times the reflection coefficient. We have to square this and divide by 2 Z0 again. And this could be rewritten like, first the voltage at the input squared, the magnitude of the voltage at the input squared, divided by two impedances, wave impedance, characteristic impedances of the line. And now we have got the input voltage out before the bracket, so what is left there is 1 minus R squared. I'd better put it in this manner. So it is amended by a factor 1 minus R magnitude squared. So now this is the power that remains in the load. There is some power carried from the generator to the load, but some is reflected back. So only that part of the power that does not reflect back remains in the load and therefore causes heat or drives the input circuit of the amplifier, so it gets propagated, amplified to the output or elsewhere. So this is an important point. That what gets reflected is not delivered to the load. Like, for example, if you come to sunlight, the sun is shining more or less constantly. So it delivers some power per square meter, possibly to you. And you have several choices. You can get a black suit. In that case, most of the power would not get reflected. It gets absorbed. And you will be quite warm. Or you can wear white suit. In that case, most of the light would get reflected. And therefore, it will not hit you. It will be carried from the sun to you all the distance of 150 million kilometers. But then it would reflect and go back. No heat to you. And that's the same with a transmission line. If there is an impedance mismatch that causes standing wave ratio, it would cause some part of the power to be reflected back. That's it. Did I help you?
Yes, thank you. And also, like the last part there, this V, like after this equation.
After this, what I have done. So the reflection coefficient has been identified as far as I remember, 1/3. When I raise it to second power, I get 1/9, and if I subtract that from 1, I get 8/9. So.
Okay, yeah, I got it's 8/9. Okay.
And that applies to the input voltage, but unfortunately we could not put there as much voltage as we have we could in the case of a DC power, because the standing wave ratio has increased the maximum over the input voltage. So now I have to input the value of the input voltage, which is 3/4 of the maximum voltage. And there should have been the second order here. And now if I raise it to second power, it's 9/16 of the original square of the input voltage. We have to multiply it by 8/9, and that's the resulting number. So this is the ratio that decreases the maximum power due to standing waves. So this is a decrease against this value for AC current. So that would be again halving the power that is delivered to the load for the case of a 100 ohm load terminating a 50 ohm cable.
Yeah, thank you very much. Yeah, I understand.
Okay, so I think we deserve another 5 minutes break. Then there will be again time for questions, because this was not as easy. And then we will switch to another topic.